In section 5.2, we're going to look at systems of linear equations in three variables. We're going to first verify the solution of a system of linear equations in three variables. Then we're going to solve a system of linear equations in three variables. Then we're going to solve an applied problem using systems in three variables. Systems of linear equations in three variables and their solutions. In general, any equation of the form ax plus by plus cz equals d, where a, b, c, and d are real numbers, such that a, b, and c are not all 0, is a linear equation in three variables x, y, and z. The solution of a system of linear equations in three variables is an ordered triple of real numbers that satisfies all equations of the system. The solution set of the system is the set of all its solutions. So an equation in x, y, and z in tree space is a plane. What's a plane? Well, in tree space, if you have a sheet of paper represents a plane. And if you have three planes and they intersect, they're going to intersect at a point in space. And that point in space can be described by using an x-coordinate, a y-coordinate, and a z-coordinate. All right, let's first determine if an ordered triple is a solution to a system of equations in three variables. Now, when we looked at an ordered pair in a system of two equations, we substituted the ordered pair into the two equations and made sure it satisfied both equations. If it's an ordered triple and a system of equations in three variables, we're going to substitute x, y, and z into all three equations. So in an ordered triple, the first coordinate in an ordered triple is the value x. The second number in the ordered triple is the value for y. And the third number in the ordered triple is the value for z. So in our ordered triple, x is equal to -1, y is equal to -4, and z is equal to 5. So we're going to substitute these three values into all three equations and make sure that all three equations are satisfied. So let's try the first equation. So I'm going to replace x with -1, y with -4, and z with 5. Does that equal 22? All right, so I get -1, -2 times -4 is 8, plus 15. Is that equal to 22? Well, -1 plus 8 is 7, 7 plus 15 is 22. So it satisfies the first equation. Let's try the second. All right, we're going to replace x with -1, y with -4, and z with 5. And we're going to see, do we get 5? So 2 times -1 is -2. -3 times -4 is plus 12. Well, it looks like I have -2 plus 12 is 10. 10 minus 5 is 5. So yes, it satisfies the second equation. Now let's check the third. I'm going to replace x with -1, y with -4, and z with 5. And I ran myself out of room. Does that equal -32? Okay, we get -3 minus 4 minus 25, and that is equal to -32. So since it satisfies all three equations, then it is a solution to this system of equations. All right, how do we solve a system of linear equations in 3 variables? We're going to do it by eliminating variables. Step 1, reduce the system to 2 equations in 2 variables. This is usually accomplished by taking 2 different pairs of equations and using the addition method to eliminate the same variable from both pairs. Solve the resulting system of 2 equations in 2 variables using addition or substitution. The result is an equation in one variable that gives the value of that variable. Back substitute the value of the variable found in step 2 into either of the equations in 2 variables to find the value of the second variable. Use the values of the 2 variables from steps 2 and 3 to find the value of the third variable by back substituting into one of the 3 original equations. Then check your proposed solution. All right, so let's solve the system. Get my mirroring to work again. There we go. Let's solve the system. X plus 4y minus z equals 20. 3x plus 2y plus z equals 8. 2x minus 3y plus 2z equals -16. All right, so to solve a system of 3 linear equations in 3 variables, you want to eliminate one of the variables. For example, you could take the first 2 equations and you could eliminate x, y, or z, any of those 3. Once you've eliminated either x or y or z from the first 2 equations, then you pick any other 2 equations, any of the other 2. So you could pick 1 and 3 and eliminate the exact same variable you eliminated from 1 and 2. Or you could take equations 2 and 3 and you could eliminate the exact same variable that you eliminated from 1 and 2. So pick any 2 equations and eliminate one of the variables. Then pick any of the other 2 equations and eliminate the same variable from those 2 equations. Then you are going to have a system of linear equations in 2 variables. You solve that for your 2 variables and then back substitute to find your third. All right, looking at this, it appears to me that the easiest variable for me to eliminate would be z. If I pick the first 2 equations and simply add them together, -z plus z will give me 0. So the z will be eliminated. So that's what I'm going to do. I'm going to pick the easiest variable for me to eliminate, and that appears to be z. So I'm going to add the first 2 equations together. Get rid of my tool. There we go. So I'm going to add the first 2 equations together. to eliminate Z. And you'll notice that I put a line through my Z. That's simply because I write 2's exactly the same way. So to distinguish between a 2 and a Z, I put a line through the Z. Okay, so I'm going to add x plus 4y minus Z equals 20 to 3x plus 2y plus Z equals 8. And so I'm going to obtain an equation in x and y. 4x plus 6y equals 28. So there's my first equation in x and y. So now I'm going to either pick the first and the third equations and eliminate Z, or I'm going to pick the second and the third and eliminate Z. Now it appears to me that if I multiply the first equation by 2 and then add that to the third, that would be an easy way for me to eliminate Z. So I'm going to multiply the top equation, the first equation, both sides by the number 2. All right, when I distribute the 2 across, I get 2x plus 8y minus 2z equals 40. And now I'm going to add that to the third equation. When I add those two equations together, I get 4x plus 5y equals 40 minus 16 is 24. So there's my second equation in 2 variables. Now I have a system of equations in 2 variables, x and y. I'm going to solve that system. So the system I'm going to solve is 4x plus 6y equals 28, and 4x plus 5y equals 24. Those are the 2 equations I got when I eliminated Z. Looks to me like I could multiply the second equation by -1 and add it to the first. I could certainly multiply the first equation by -1 and add it to the second. Either one is going to eliminate the x. And I like positives, so I'm probably going to multiply the second equation by -1 and add it to the first. So I'm going to multiply both sides of the second equation by -1. And I get, when I distribute that -1 across, -4x minus 4y equals -24. Then I'm going to add that to the first equation. 4x plus 6y equals 28. When I add those 2 equations together, I get y equals 4. Now that I know what y is, I can back substitute into either one of these equations and find x. So why not just pick the first equation? 4x plus 6y equals 28. 4x plus 6 times 4 is 28. 4x, 6 times 4 is 24. Subtract the 24 from both sides. I get 4x equals 28 minus 24 is 4. Divide both sides by 4, and I get x is 1. So my ordered triple, the y is equal to 1, and the y is equal to 4, and x is equal to 1. Now that I know x and y, I'm going to back substitute in one of my 3 original equations and find z. So here are my 3 original equations. I have x is 1 and y is 4. I pick any of the 3. And, 1/6 of one, half dozen of the other. I think the second equation's the easiest because the coefficient in front of the z is +1, so I think I'll choose that one. I'm all about finding the easiest way to do this. I'm going to replace the x with 1, the y with 4. I get 3 plus 2 times 4 is 8. Oh, left off my z there. So I get 11 plus z equals 8. Subtract 11 from both sides, and we get z. 8 minus 11 is -3. So the solution to this system of equations is the ordered triple. X is 1, y is 4, z is -3. 1, 4, -3. And I really should check this solution to make sure it works. Replace the x, y, and z in each of the equations with 1, 4, and -3, and make sure that it satisfies each of these three equations. All right, so this is how we solve a system of linear equations in 3 variables. Pick any of the 2 equations and eliminate either x or y or z, whatever is easiest for you to eliminate. Then pick any of the other 2 of the 3 equations and eliminate the same variable from those 2 equations. That will give you a system in 2 equations and 2 variables. Solve that system either by substitution or addition. That'll give you 2 variables. Once you have 2 variables, you can back substitute and find the third. Let's solve an application. Find the quadratic function y equals ax squared plus bx plus c, whose graph passes through the points 1, 4, 2, 1, and 3, 4. All right, so what I don't know in this application, I don't know what A or B or C is. However, I have 3 ordered pairs that tells me what x and y are. The first ordered pair, 1, 4, says that this graph goes through the point x equals 1, y equals 4. So I can substitute that back into the quadratic function and find an equation in A and B and C. So for the ordered pair 1, 4, I'm going to substitute that into my equation. So y is 4 and x is 1. So my first equation is 1 squared is 1. 1 times a is a. B times 1 is b. So my first equation is a plus b plus c equals 4. All right, to find the second equation, we're going to use the ordered pair 2, 1 and do the same thing. So x is 2 and y is 1. Two squared is 4. 4 times a is 4a, plus 2 times b, plus c. So my second equation in a, b, and c is 4a plus 2b plus c plus 1. So there's equation 2. To find equation 3, I'm going to replace x and y with 3 and 4. So y is 4 and x is 3. So I get 4. 3 squared is 9. 9 times A plus 3 times B plus C. So my third equation is 9A plus 3B plus C equals 4. So I now have a system of linear equations in 3 variables. I have 3 equations, 3 variables, A, B, and C. So here is the system of equations I'm attempting to solve. A plus B plus C equals 4. 4A plus 2B plus C equals 1. And 9A plus 3B plus C is equal to 4. Now, it appears to me that the easiest thing to eliminate would be C. I could multiply the top equation by -1 and add that to the second and eliminate C. I could multiply that top equation by -1 and add it to the third equation and eliminate C. So that's what I'm going to do. I'm going to multiply the first equation by -1, both sides. And I obtain -A minus B minus C equals -4. And then I'm going to add that to equation 2. And I get 3A, 4A minus A is 3A, -B plus 2B is plus B, and then I've eliminated the C's. Minus C plus C is 0, -4 plus 1 is -3. So there's my first equation in 2 variables. Now I'm going to add that equation that I multiplied by -1. I'm going to add that to equation 3. Okay, so I had -A minus B minus C equals -4, and I'm going to add that to equation 3. And again, I'm going to eliminate C. 9A minus A is 8A. 3B minus B is 2B. C minus C is 0. 4 minus 4 is 0. So now I have my second equation in terms of A and B. And I don't think that's what I have on this slide. I changed things up a little bit. So what did I have? 8A plus 2B equals 0. I think in my original thought was to eliminate C from equations 2 and 3. Okay, so now I have 2 equations. So it looks to me to be able to solve this if I multiply the top equation by -2, then I could eliminate the B. So let me try that. So I get -6A minus 2B is equal to 6. I'm going to add that to the second equation and eliminate B. And I get 2A equals 6. Divide both sides by 2. And I get A is 3. So the coefficient on the x squared in my quadratic function is the number 3. Now I can find B by substituting A equals 3 into either of these 2 equations, and I'm going to choose the top one. So I'm going to replace A with 3. Nine plus B equals -3. I'm going to subtract 9 from both sides, and I get B is -12. So now I have the coefficient on the x squared in my quadratic function, that's 3, and the coefficient on my x in my quadratic function is -12. So now I would need to find C. So I'm going to back substitute A is 3 and B is -12 into any of my 3 original equations. and I'm going to find C. So here are my original equations. I'm going to back substitute, and I would pick the first equation. That would be the easiest one to back substitute. So what did we have again? We had A is 3 and B is negative 12. So I get 3 minus 12, that's minus 9. Add 9 to both sides, and I get C is 13. So now I have the coefficients on my quadratic function. Y equals ax squared plus bx plus c. I know a, b, and c now, so I can make those substitutions. So my function is 3x squared minus 12x plus 13. That is the quadratic function that goes through those three ordered pairs. And that's the end of section 5.2.